Professor Sprott, somewhere in the universe.
Is that you, Lovell?
You look like you're in outer space.
I'm indeed in space, near the planet Saturn. But that's not the surprise. The surprise is that I'm going back in time to fetch Albert Einstein.
To go back in time, you're going to have to go faster than the speed of light.
This is a very fast rocket. I found the plans on the internet, and so what could go wrong?
I suppose we get to see this historic flight. Bless my slide rule. That thing is actually moving with a paddle yet. Wait till NASA hears about this. Point 2, point 2.5, point 3, 0.35, point 4, point 4.5. It's Lorentz-Scale contraction. Sprott really isn't getting flat in his frame of reference, but he sure is in ours. Well, look at that. He's redshifting. Good grief. 0.75, 0.8, 0.85, 0.9, 0.95. It's the historic. That sounded like it came from back there. Let's take a look. Aha! Pay no attention to the man behind the curtain, indeed. Ladies and gentlemen, I give you, at considerably less than the speed of light, Professor Clint Sprott.
Welcome to the wonders of physics. Now, of course, I didn't really travel at the speed of light, and I didn't go back in time to fetch Albert Einstein. But we are celebrating the miraculous year that he had in 1905, when he laid down many of the principles of physics that we have today. And, you know, he's visited us almost every year, and so I wouldn't be surprised if he dropped in on us today, too. But one of the things he did was to revolutionize our understanding of space and time. And I would like to show you a demonstration that involves space and time. And for this, I need a volunteer. Okay. How about you? Come down here. Face the audience. What's your name?
Billy.
Billy? Billy, would you like to earn $1?
Yes.
You have to earn it. I didn't say would you like to have it. I said would you like to earn it. You know, Billy, $1, it has a picture on it. You know who that is?
George Washington.
George Washington. Who was he?
First president.
First president, that's right. Well, Billy, this is really quite easy. All you have to do is hold your fingers in front of you about that far apart. Can you do that? Right like that. Just opposite George Washington's picture on the dollar bill. Okay? Now, what I'm going to do is drop the dollar bill, and all you have to do is catch it. And if you catch it, you can have it. Are you ready?
Yeah.
Oh, can you pick that up, Billy? I'll tell you what, you can have the bill. Now, I was pretty sure he couldn't catch the dollar bill because it's about 7 centimeters from the end of the bill to George Washington's picture. And it takes about 1/10 of a second for something to fall 7 centimeters. And most people's reaction time is at least 2/10 of a second. And so very few people could do that. In fact, you could do an experiment yourself at home. If you have something like a meter stick or a yardstick or even a foot ruler, if you hold it and have one of your friends hold their fingers opposite the 50 centimeter mark and then drop it and see how far it falls before they catch it, you will, in essence, measure their reaction time. The farther it falls, the slower their reaction time. So these are some examples of the physics of motion. And I want to show you another example of motion that involves this gadget right here. It's something that looks like a baseball. And this baseball is on the end of an arm that can swing around. And the baseball is attached to the arm with a very fine thread. And what I'm going to do is turn on the motor and let this go round and round. Now, when it comes to this point right here, there's a very sharp knife blade. And what I'm going to do is turn the knife blade so it comes up and cuts the string. And you may think what you suspect will happen as this ball goes round and round when the string is cut. The ball is going to fly off, but in what direction do you think it will fly? Well, let's do the experiment. So we'll turn it on. Goes around nice and fast. And I have to be careful when I do this. And you notice it went in that direction. And that is easy to predict. Now, many people would think, since the ball was going round and round, maybe when the string was cut, it would keep going around for a little while. But in fact, it doesn't, because of Newton's first law of motion, the so-called law of inertia. An object moving in a certain direction will continue moving in that direction as long as there are no forces acting on it. And at the instant the string is cut, all the forces are removed. There's a force of gravity that made it fall, but there is no force pulling it in toward the center of the circle, and so it had to keep going in the exact direction it was going at the instant the string was cut. And so this is an example of the physics of motion that we call Newton's first law, named after Isaac Newton, who of course predated Albert Einstein by quite some time. Now, another example of the way things move and the way things go around, you may wonder, when the universe was very young, it was made up of gases that sort of like the air that you're breathing right now. And eventually those gases coalesced and condensed into galaxies and stars and even planets. And as you know, the Earth rotates on its axis. In fact, almost all of the astronomical bodies that we know about are rotating. Even galaxies themselves rotate. You may wonder where all that rotation came from. And I can illustrate that with this gadget up here, called a Hoberman sphere, and I'm going to set it into a very gentle rotation. So you can imagine the gas in the early universe very gently rotating like that. And as it collapsed to form galaxies and stars, you may wonder what would happen. Well, I can actually make this collapse by hanging a weight on it. And you see how it goes around very fast now. And the reason for that is familiar to most of you. Have you seen an ice skater go out on the ice with her arms out like this and spin around and then bring her arms in and go really fast? It's the same principle, the conservation of angular momentum. And so if I open it up again, you can see the rotation slows. And I can keep doing this over and over. Every time I contract it, it rotates fast, and then when it expands, it rotates slowly. Now I want to show you another demonstration that involves motion. Here I have a long, hollow pipe. And at this end of the pipe, can you see what this is? It's a ball. It's a ping pong ball, in fact. And right now there's air in the pipe. And what I'm going to do is to pump all of the air out of the pipe. On the two ends of the pipe is a little piece of plastic that allows me to evacuate the pipe. To do that, we'll turn on the vacuum pump over here. And you can see by the gauge the pressure coming down towards zero. Now, it's very hard to get every little bit of air out, but fortunately we don't have to. We just need to get most of the air out of the pipe, as we have now done. So when the pressure comes down to a low value like that, I can then close this valve right here. Once I've done that, I can turn off the vacuum pump and, in fact, let air into the vacuum pump. And we have this long pipe with little or no air in it. Now, as I said, on the two ends is a thin piece of plastic. And what I'm going to do is take some scissors, very sharp on the ends, and I'm going to puncture this piece of plastic on the end. The air will rush in, and it will push the ball forward. Now, you notice Mr. Lovell with his fingers in his ears? If loud noises bother you, you may want to do the same. And I'm going to put on my ear protection, too. Is everyone ready? Yes. And you notice the ball went all the way down and hit one of these cans, and in fact went right into the can. And it made a hole in it, and the ping pong ball is trapped down there. So that shows you how very large the forces can be that are resulting from the air pressure. It's about 15 pounds for every square inch. And so that propelled the ball very, very rapidly. Oh my goodness. Are you Albert
No, I'm Professor Willie Haverly.
Oh, but you look exactly like Albert Einstein, and we were expecting him today, but indeed, Albert Einstein is Swiss. Where are you from, sir?
Oh, I'm from Switzerland.
Oh, you're from Switzerland, too. Well, do you have a brother named Al?
No, I'm just looking for a seat.
Oh, I see. Well, okay, I'm sorry I mistook you, but Albert Einstein was a physicist, and what would you be?
Well, I'm a physicist.
Oh, Professor Haberle, you said. Well, you didn't by chance long ago publish a paper on Brownian motion, did you?
Oh, long time ago. Long time ago. Yeah, in the Zeitschrift für Physik.
Really? Like 100 years ago?
Just about.
Huh. Well, now this is an amazing coincidence because Brownian motion is one of the famous papers that Albert Einstein wrote. Would you help us demonstrate Brownian motion?
Well, if you insist.
I do. Over here we have a jar that has some smoke in it. And what we're doing is running some of the smoke under a microscope, and we're displaying it on the television monitor. And what you're seeing are tiny particles of smoke. Could you explain what's happening?
Oh yes. Well, you see these little smoke particles. They're jiggling around back and forth. And the question was that people didn't know why that was. And the explanation is that these are tiny smoke particles, but they are hit by even tinier air molecules. But the air molecules are so small you don't see them. But now sometimes there are a few more air molecules hitting it from one side, sometimes from the other side, and so this makes this jiggly motion. And you know, that was at the time important because even scientists didn't all believe that there were atoms in the air because we couldn't see them. And here we see how the atoms hit these smoke particles.
Well, that's very fascinating, Professor Haberle, and I'm delighted that you came in at this point to explain this to us. And I think I saw a seat over there you can take if you'd like to do so.
Did you say I could take a seat?
Yes, please. Well, I guess I'm a little embarrassed. I was certainly expecting Albert Einstein, and he looked a lot like him, but apparently not. But it was quite a coincidence. But it is true that the molecules in any substance, even the air you're breathing, are in very rapid random motion. And of course, molecules are too small for you to see, but I can show you a demonstration. On the screen here, you see a bunch of ball bearings, several dozen ball bearings that are sitting in a little trough. And on the top of this is a partition that's just resting on them. And on the bottom, there's a plunger that's connected to a loudspeaker, much like on your stereo set at home. And what I'm going to do is turn on an audio oscillator that will bounce the ball bearings up and down at about 30 times a second. And you can see they begin moving very rapidly, sort of a random-like motion. And this is a little what you would see if you could see the individual molecules of the air moving around, a little like in the Brownian motion. And you notice a peculiar thing. When I turn the volume up on the speaker, as I'm now doing, they move more rapidly. And this is analogous to increasing the temperature. So this is what a gas at high temperature would look like, and this is what a gas at low temperature would look like. And do you notice that as I turn up the temperature, the volume of the gas increases? And you probably know that happens. When you heat most anything, especially gases, they expand as they get hotter, and then they contract as they get colder. So, of course, these are not actual air molecules, but they do simulate what you would see if you could see molecules. Now, a very familiar gas that most of you have at home is called natural gas. And maybe you heat your home with it, or maybe you use it for cooking. And natural gas, chemically, is something called methane. For you chemists, it's CH4. And methane has recently become sort of important because there's a spacecraft right now orbiting the planet Saturn, where I was earlier, and it sent a spacecraft, a probe, down to one of the moons of Saturn called Titan. And they discovered evidence on Titan of rivers and of lakes, but not made of water, made of liquid methane. And normally methane is a gas. And so I thought I would show you some liquid methane. And in order to do that, we have to start with methane gas. And I have here natural gas, and I'm going to flow that into this tube that goes into this glass apparatus right here. Now, to make liquid methane, you have to cool it. And in order to cool it, I'm going to use a substance here that is called liquid nitrogen. Nitrogen, of course, is what makes up most of the air you're breathing. About 80% of the air you're breathing is nitrogen. But if you cool nitrogen sufficiently, 321 degrees below zero, it will become a liquid. And so the methane which is in here will liquefy, and it will drip into this little flask on the bottom. Now, to prevent it from just boiling away, once it gets in the flask, I'm going to cool the flask down and put a little more liquid nitrogen in up here in order to make some liquid methane. So we're cooling down the methane gas in order to make a liquid using this liquid nitrogen. Now, liquid nitrogen is probably the coldest stuff you've ever encountered. It's a mere 77 degrees above the absolute coldest that anything can be. And now it's hard for you to see, but I have collected about a 1/4 inch of methane in this little flask on the bottom. Now, in order to prove to you that it's methane, I need to remove it and show it to you. Now, I don't dare touch this with my fingers because it's much too cold. But what I can do, first of all, I'll turn off the gas because we've collected enough now. And then I will disconnect the hose. And we can remove the flask of liquid nitrogen. And by putting on my gloves, I can move the flask aside, as I will do. And now we have this little flask that has a little bit of liquid methane in it. And so I can take this off. And it's a little hard for you to see, I know. But in here is about a 1/4 inch of liquid methane. Now, to convince you that it really is liquid methane, I can do an interesting thing. As you know, methane is a flammable gas. And so I can make a fire here, and you see it burns. Now, you may wonder why it's burning. Well, it's burning because methane is a flammable gas. And, of course, gaseous methane is the same natural gas that you have in your homes. And so as it begins to evaporate, the gas comes off, and it will burn for quite a long time.
Excuse me.
Excuse me. Can I help you?
Have you seen my papa?
Your papa? Who is your papa?
Professor Albert Einstein.
Oh. Well, no. We're expecting him today, but he hasn't been here yet.
Are you sure?
Yes, we haven't seen him, but if he's your papa, then you must be his daughter.
Oh, sorry. I'm Elsa Einstein, his stepdaughter from his second marriage.
Ah, I see. And what is it like to be Albert Einstein's daughter?
Oh, it's great. But you know, even the really smart are still just human. Papa likes to tell funny stories of himself that aren't always flattering. Such as when he fell out of a chair at the Swiss patent office and created general relativity.
I don't think I ever heard that.
Have you ever heard how he came up with the bad airplane?
Albert Einstein invented a bad airplane?
Ah, yes. He calculated that it was Bernoulli's principle that caused a wing to have lift. He made a humpback wing and convinced a German aircraft company to fit them onto one of their planes.
Well, you know, I know about the Bernoulli effect. In fact, sometimes we do a little demonstration of the Bernoulli effect. Here are 2 sheets of paper, and they're hanging from above. And what I often do is blow between the sheets of paper and ask people what they think will happen. Do you think the pieces of paper will fly apart? Who thinks that? Who thinks they will pinch together? Well, let's try it. And you see it does pinch together, and that's the Bernoulli effect that allows airplanes to fly.
It's a cute demonstration, but what Papa forgot is that you have to minimize drag in the wing in order for it to work properly. The plane only had 2 brief flights, and the pilots were both very, very scared. One of them said it flew like a pregnant duck.
Well, that's a fascinating story, and you know, it is reassuring to know that even Albert Einstein occasionally made mistakes.
He said, what was it? Oh, this is what happens to a man who thinks a lot but reads little. My father never did do his homework.
I've heard that. Well, it's a great honor that you visited us today,
Thank
and
you.
if we see your father, we'll certainly tell him you were here.
Thank you. Bye.
Well, I'm sure Albert Einstein will be here eventually, but we were talking about gases of various sorts, and I have a little jar over here that has a gas in it, and the gas is ordinary air. Now, you may wonder why we have a jar of air, and it's because I want to take an object and put it in the jar. And the object is a little tiny balloon that was blown up before the lecture and tied off. And I'm going to ask you what you think will happen when I put this balloon in the jar and then remove the air. Who has an idea? You think it will float up? What do you think? It'll pop? Bounce around in the jar? These are great answers. You have an answer? It will explode. That's sort of like popping, isn't it? Expand. Anything else? Stay the same? That's a good answer. What do you think? It'll shrink. Well, you know, there's lots of answers, aren't there? But you know, in science, we don't just argue about things. We do the experiment. So let's put this in this jar. We'll just set it right there. And yeah, we have this on the television there, so you can watch it up there if you can't see it down here. So I'm now going to turn on the vacuum pump and remove most of the air from this tube, from this, from this jar. So you see the pressure coming down. Can you see anything happening? It's getting bigger, isn't it? So those of you who thought it was going to expand were in fact correct. It's not floating. It hasn't popped, at least not yet. If we let it get big enough, maybe it would. What do you think would happen now if we turn the vacuum pump off and let air back in? That's right. You think it would shrink again. Well, let's try it. Watch up there. And so you're right. It does shrink back to the original size. Now, if you think about it, the size of a balloon is determined by three things. It's determined by the pressure of the gas inside. Well, that didn't change. We had it sealed off. It's determined by the elasticity of the rubber that's trying to contract it. That didn't change. But it's also determined by the pressure of the air around it. And that did change. So by reducing the outside pressure, that allowed the balloon to expand. And then when we put the pressure back in, it contracted again. Now, there are many things we could put in there. How about we put some of these in there? You like that idea, don't you? Okay. So we'll remove the balloon. We'll take one of these marshmallows. We'll put it right there. Now, what do you think will happen? That's right, it's getting bigger. Now, what do you think will happen to the marshmallow when I turn off the vacuum pump and let air in? So you notice that it expanded, just like the balloon did, and that's because a marshmallow is a lot of little tiny balloons. You know, a marshmallow is mostly air, and the air is inside in little tiny cavities, and when we remove the outside air pressure, then those balloons expanded, just like the big balloon did. But these balloons are a little bit leaky, so after a little while, the air leaked out of those balloons, and then we had a partial vacuum inside the marshmallow. And then when we let the air in, it crushed the marshmallow. But it is an ordinary marshmallow. In fact, it tastes pretty good. Now, speaking of jars with vacuums in it, I have a jar here with something in it. What is this? A bell. That's right. It's a bell in a jar, and the jar has air in it. And what I want to do is shake the jar and let you listen to the air, or let you listen to the bell, sorry. Can you all hear that? It's not very loud because it's inside of a jar. You may wonder why I put a bell on a jar. And the reason is that I now want to remove the air from the jar. And we'll see if that changes the sound. So to do that, we use the same vacuum pump that we used before. And you see the pressure coming down towards 0. And it takes a long time for it to get all the way down to 0. In fact, it would take forever, so we won't wait that long. But when it gets down low enough, we can then close this valve right here. And then we don't need the vacuum pump. We can turn that off. In fact, we can let air into the vacuum pump. And then we can remove the hose from the jar. And what do we have in the jar now? A bell? No air? Less air. All good answers. There's a little bit of air. We call it a partial vacuum. But the interesting thing is what happens when I shake it now. So listen and see if you can hear it. It's really very hard to hear now. It's making almost no sound. Now to show you there are no tricks, I can open the valve and let air go in, and I'll try to shake it while I'm doing that, and you'll hear the sound come back. So that illustrates to you that sound is a wave, and it needs a medium through which to propagate. When I'm talking and you're listening, it's because I'm making waves in the air that's in this room. And if there were no air in the room, you wouldn't be able to hear me. Well, you'd be dead, in fact, wouldn't you? But in that brief moment before you succumbed, you would not be able to hear me. And so waves are very common in nature, and there are many examples of waves. And I want to show you another example of a wave that you're all familiar with. I have here a long rope, and on one end it's attached to the wall. And I'm going to stretch it out, and many of you have probably done this with a rope or maybe a garden hose. And if I stretch it and give it a flick with my wrist, I can make a wave that moves down the rope. So let's do that. Now you see a curious thing. When the wave gets to the other end, it in fact reflects and comes back. You notice that? And in fact, when it hits my hand, it reflects again, and the wave goes back and forth along the rope. Now you've probably all done that, and that's familiar to you, but you may not have looked carefully at what happens to the wave when the rope has very little tension in it, as it does now. You see the wave moves relatively slowly. It takes a long time to get down and come back, but if I pull hard on the rope, give a lot of tension, the wave moves much faster. And in fact, the speed of the wave is proportional to the square root of the tension in the rope. So that's a familiar idea and probably is of no great surprise to you. But I want to show you another demonstration that involves waves traveling on a rope. You see over here we have two ropes. The upper rope is a 1/4-inch rope, very small, and the lower rope is a 1/2-inch rope, much bigger. And these ropes are under exactly the same tension. How do I know that to be the case? Because down at this end there's a pulley, and the rope goes around the pulley. So they're being pulled with the same tension. But one rope is a light rope and the other is a heavy rope. Now who thinks the wave will travel faster on the light rope on the top? Who thinks it will travel faster on the heavy rope on the bottom? A few people. So most people think the light rope will have the greater wave speed. Now to make a wave on the rope, I have to somehow start the wave at the same time on the two ropes. The way I'm going to do that is to take a meter stick, and I'm going to hit the two ropes at the same instant. Now you notice Mr. Lovell has put a couple of index cards on the rope down at the other end. There's a red one on the top and a blue one on the bottom. And what you're going to see is as the wave moves down there, those cards are going to jump off the rope. And the card that jumps off first, obviously, is on the rope that has the greatest speed. So don't watch me. Watch the cards down there. and I'll tell you when I'm going to hit it. 1, on 3, 2, 3. Now, I hope it was obvious that the wave traveled faster on the light rope than on the...
Albert, are you here? Albert?
Excuse me, can I help you?
Oh. Hi, I'm looking for Albert.
Albert who?
Albert Einstein.
Oh, well, you know, we were expecting him, but he hasn't been here yet.
Oh, well, he told me he was playing here today. I'm his second wife, Elsa. I
Ah.
brought his violin.
Ah, I see that. Well, I know he is very forgetful.
Well, yes, he is a little absent-minded. Sometimes he plays his violin right through dinner. And when he's chatting with his cronies...
He has cronies?
Oh, I'm sure you know Bohr and Boltzmann, Lorentz, Planck. And who's that fellow who's always standing on his principal?
Mach?
Yes, Mach, right. But it's very entertaining as well. The other night, Newton was over for dinner. You know Newton. And Albert was teasing him about overthrowing the Newtonian worldview. And Newton said, Albert, I would have seen farther if it hadn't been for all those giants standing on my shoulders.
Well, that's a fascinating story. I don't know whether I believe it, but anyway, I notice you're dressed rather formally. What is the occasion?
Yes, we're going to see that new play, Phantom of the Opera, after your show.
Mm-hmm. Well, you know, I hear the tickets for that are as hard to get as for the wonders of physics.
Well, you know, since we're dead, we don't worry about tickets that much.
Well, that's a good point. Well, it's great that you came to visit us, and if you want to stay and wait for him, you're welcome to do that.
Oh, I would love to do that. Thank you.
Okay, you can do that. You can take a seat over there, and you could give your violin to Mr. Lovell, and when your husband comes in, we can give it to him. But I was making the point that sounds have very complex wave shapes. And this is what a sound wave would look like if you could actually see it. Of course, normally sound waves are invisible to you. And this wave is coming from the sound that this microphone is picking up. And you can see how complicated the wave associated with human speech is. But there are other sounds that are much simpler. Do you recognize this object? It's a tuning fork. It's a little U-shaped piece of metal. You strike it with a mallet, and it makes a sound. And I'm going to do that and let you see what the sound looks like on the oscilloscope. And you see what a very regular kind of wave that is. That's something called a sine wave. It's the purest form of wave. Now, there are many ways to make sounds. I have here a Coke bottle. You don't see many of these anymore. But you may have had the experience of blowing over the top of a bottle and making a sound. Have you done that? But I bet you haven't done it when you had an oscilloscope to look at what the wave actually looked like. So let's try that. And you see, it's sort of a sine wave too, but it also has some noise on the top of it. Now here's another Coke bottle that's just the same as the other, except this one has water about up to the halfway mark. What do you think will happen when we blow over this? Let's try it. You see, it makes a higher pitch. And that's because the column of air that's vibrating in this is only about half as long as the column of air that's vibrating in this. And that shows that the frequency of a sound is related to the wavelength of the sound. The shorter the wavelength, the higher the frequency and the higher the pitch of the sound. Now, there are many other sounds I could show you, and in fact, every musical instrument makes a distinctive sound. And you can often tell one musical instrument from another just by listening. And I can illustrate that if we had a musical instrument. I wonder if Albert Einstein would mind if we used his violin for a demonstration.
Oh, I think he would be delighted. You know, it's quite a valuable violin, but as Albert always says, everything's relative.
Well, that's great. Is there anyone that plays the violin? You don't have to be really good at it, but you do have to play a few notes. Would you come down here? Turn around. What is your name? Lily. How long have you been playing the violin, Lily?
Since the beginning of 2005.
The beginning of 2005. That was a long time ago, wasn't it? Okay. Are you big enough to play this violin? It's almost bigger than you are. Okay, can you take it? Now be careful with that. That belongs to Albert Einstein. Would you come right over by the microphone over here, Lily? Stand right about here and just play a few notes for us, if you would. That's beautiful, Lily. Thank you so much. And one reason a violin sounds so pleasing to you is that it has not a single frequency, but it has many different frequencies. And the frequencies are related to one another. So they're like twice and 3 times and 4 times the fundamental frequency. And that's an example of what we call a harmonic sound. And that's why the violin sounds so harmonious to you. Now, there are many other things. In fact, all musical instruments make a spectrum of frequencies, but they're not all harmonically related in that way. And I have here another gadget that is like a musical instrument that perhaps you've never seen before. It's a piece of aluminum, and it's got a hole in the middle. It's a little like a big washer, isn't it? And I can strike this with a mallet, much as I did with the tuning fork, and it will make a sound. But the sound is not a sine wave, like it is with the tuning fork, but it's more complicated. So I'll do that and let you see what it looks like on the oscilloscope. So you see it's made up of several different frequencies, but the frequencies are not harmonically related. We call those overtones, and every musical instrument has overtones. Even a drum has overtones, but they're not harmonically related. And so look what the drum looks like. A very complicated wave shape indeed. Now, there's one other thing I can do with this. I can just put it down on the floor and give it a spin. My goodness, what is this?
It's my rocket.
Rocket? This is no rocket, this is a tricycle.
Ah. Huh? Just wait, here we go. Ah. Plots! Plots! Ah.
That's the most feeble rocket I've ever seen.
Mein Rocket! Mein Rocket ist kaputt! Der Dummkopf in the tuxedo, this is mein Rocket. Ah! This rocket was built by Albert Einstein.
Albert Einstein? Built
Yes.
rockets? You knew Albert Einstein?
Ah. Albert Einstein is only your brother.
Your brother? You're
Ich
Albert...
bin Buck Einstein von der 19th century.
Buck Einstein?
But mein Rocket is kaputt.
Well, well, it's not my fault. Maybe it's your brother's fault. But the 19th century, what are you doing here today?
Mein Rocket, Albert said to me, Buck, get out.
I can understand why, but go ahead.
So I got out.
I see that.
I went to see Saturn, and I went to see the Pleiades.
I was at Saturn just earlier today, but...
Yeah, I can tell.
Oh, that's something that we call a computer? And you're from the 19th century?
Yeah.
Well, what are you doing here in the 21st century?
Mein Rocket?
Yeah? How long have you been gone?
1 year.
1 year? Did you know this is the year 2005?
No.
When did you leave?
No, in 1895.
1895? You must have been going very fast.
Yeah.
Well, you know, this is something predicted by your brother. He said that if you travel sufficiently fast, time would slow down for you.
Yeah?
And you would age very slowly.
Oh.
You know, your brother has been dead for over 50 years.
Oh. Well, you're so smart, Herr Doctor, Professor. Was ist alles?
Well, this is the wonders of physics, and I'm Professor Sprott, and
Yeah?
these are demonstrations. We're honoring your brother today.
Him?
Yeah.
Der
him.
Dummkopf? The dropout? Him?
Well, he was very famous. He was the most famous of all physicists.
Nein, he's nothing.
Nothing?
No. Dropout, no good, nada. Was ist das?
Oh, well, in fact, I was about to show the folks this. This is something called a Marx generator. Would you help us demonstrate it?
Yeah.
Well, you know, if you go back there to the controls and put on your ear protection, because this might make noise, everyone be careful, and I'll explain what we have. Here we have 10 capacitors. They're like storage batteries. They store up electricity. And we're going to charge them all up to about 50,000 volts. And then we're going to discharge them all in series, like the flashlight, like the batteries in your flashlight, to make 500,000 volts. And that voltage will appear between right here and right here, and it will make a bolt of lightning. A 500,000 volt bolt of lightning. So, Buck, all you have to do is turn on. You have to turn up the little dial, and then when it's all the way up, then you push the button. Are you ready?
Okay, 23 skidoo.
Everyone ready?
Eins, zwei, pickle.
Well, thanks for stopping in. And, you know, if we see your brother, I'm going to tell him you were here and that you didn't say very nice things about him.
Yeah.
We are expecting him later.
Yeah. Tell him my rocket is kaputt. You know where I can park this thing?
You know, I think you can park it right outside the door there.
All right, here we go. Ready? Flats, big.
Well, I don't know about that, but you know, Albert Einstein did predict that if you travel fast enough, time slows down for you, and in fact, you age very slowly. And it is conceivable that someone traveling at very close to the speed of light could come back many years later, much younger than his brother. Anyway, we were talking about electricity, and I have here an example of electricity. This is electricity that travels through a gas, and it does so with a beam of electrons. I have here a tube that's evacuated. It has very little air in it, and I'm going to put a very high electrical voltage between the two ends, and that's going to make some electrons leave this end, and the electrons will move down toward the other end, and they will make a glow that you will be able to see on this plastic screen behind. So let me just show you that. Can you see the green trace of the electrons which are moving through the gas right there? Now, an interesting thing is that you can affect electric currents with magnets. And I have here an ordinary magnet. You can see I can pick up nails with it. And what I want to do is bring the magnet near the beam of electrons and show you that I can steer it around with the magnet. So watch this. So I can move the electron beam around. And this is exactly the way your television set works. If you have a television set with a cathode ray tube in it, there's a beam of electrons that hits the screen. That's the thing you're looking at on the television set. And the beam of electrons is moved around within the television by magnets. They're not magnets like that, they're electromagnets, but that's the way the beam moves around to produce the moving picture that you're all familiar with. Now, electricity and magnetism are closely related, but they're different. And before the time of Einstein, actually, it was predicted that there should be waves of electricity and magnetism. A very strange sort of thing when you think about it. And people began looking for such waves. And there was a German physicist named Heinrich Hertz who, in the late 1800s, built an apparatus that's much like the one you see right here. And the apparatus consists of a loop of wire, and there's a thing called a capacitor right here. It's much like the capacitors over in the Marx generator. And there are a couple of metal balls here. And we're going to put a high voltage between these balls and make a spark, and that will induce an electric current in this loop. And so this is a little like a radio transmitter. And then, of course, Hertz lived before there were radios, so he had to think up how to make a radio receiver. And so here was Hertz's original radio receiver, or a model of it. It's, again, a loop, and there's another capacitor, and there are a couple of little metal balls right here. And when this loop picks up the electromagnetic wave, it will make a spark across there. So let's turn on the transmitter and see if we can receive the signal. So you see those sparks. And that was the first indication that Hertz had of this electromagnetic wave. And these two things are not at all connected to each other. The waves are traveling through, in fact, empty space and detected over here. And of course, Hertz was gradually able to move the receiver farther and farther from the transmitter until today we can send radio waves around the world and even to distant places in the solar system, like to Saturn. And so radio, of course, is very important to us. Now, Hertz also measured the speed that those waves moved with. And he discovered that they moved with the same speed as light moved. And it was that observation, in fact, that led Albert Einstein to come up with his theory of relativity, trying to explain how it could be that light travels at the same speed for all observers. Now, most people think Albert Einstein got his Nobel Prize for the theory of relativity. That's what we all know him for, right? But in fact, it was not for the theory of relativity. It was for something called the photoelectric effect. And the photoelectric effect is a very important experiment that people... Excuse me? I'm sorry? What? I didn't see anything. Anyway, Albert Einstein got his Nobel Prize for the photoelectric effect. And I want to demonstrate that to you. What? I don't know what you're talking about. Albert Einstein got his Nobel Prize for explaining the photoelectric effect, and I want to demonstrate that to you. I have here a rabbit's fur that was donated to us after the rabbit no longer needed it. And I'm going to charge up a rod, a plastic rod, with electricity. And you've probably all done this if you've rubbed one thing against another. You know you can make static electricity. Now on the television monitor, you see something that's called an electroscope. And it's two pieces of foil, aluminum foil, that are sort of limply hanging down beside one another. And what I'm going to do is apply an electric charge to those foils by bringing this rod up near them. Then I'm going to touch this plate, take my hand away, and then take the rod away. And those foils now have an electric charge on them. They're negative electric charges. Now, the prediction of classical physics was that a sufficiently bright light shining on this plate that's connected to the foils should discharge it, because a bright light will, should knock the electrons off the plate and discharge it. So we can just try that by turning on the light and bringing it over near there. And you see really nothing is happening. And this was a great puzzle to people. And no matter how bright you made the light, still nothing would happen. And this was quite contrary to the predictions of classical physics. But what people did observe was that if you take an ultraviolet light, and I have such a thing here, this is an ultraviolet light. Of course, what you're seeing is not the ultraviolet, but there is a lot of ultraviolet coming out of here. And of course, that's what gives you sunburn, so I don't want to keep my hand in there too long. If you bring the ultraviolet light over near this plate and watch what happens, you will see that it, in fact, discharges the electroscope. Now, this is very puzzling because this was a 100-watt light bulb. The ultraviolet light is only about 10 watts. And so it's very odd that a light that is less intense, in fact, has a bigger effect. And it was Albert Einstein who explained that, because he said that light consists not just of waves, but of tiny particles called photons. And ultraviolet light photons are more energetic than the photons that come from visible light, and that's why they're able to do that, whereas the white light is not. So I want to show you one last demonstration that involves light, and it involves something that we call optical illusions. In the upper left, do you see a vase? Or do you see two people facing each other? Well, how about in the upper right? Could you make a magnet that looks like that? It'd be pretty hard, wouldn't it? How about the Penrose triangle? Could you go into your woodworking shop and build one of those? It'd be pretty hard. And if you make one, bring it to me and we'll sell it. In the lower left are things called Necker cubes. They're just geometric figures. And if you stare at them for a while, they will appear to flip. And the back side will become the front side, and the front side will become the back side. Well, it takes a little while for that to happen. It may work for some of you, but not others. But there are many other optical illusions I could show you. Can you count the black dots? There aren't any? There are no black dots? Well, count the white dots then. 5? That's pretty weird, isn't it? Now, this is not a trick we're doing with the computer. This is something that's happening in your brain. And it is an optical illusion. It's something that looks one way but is another. What does this look like to you? Does it look like there's a rectangle floating above the other rectangle, the background? If you move your head from side to side, you may see it better, or up and down. You see it. Good for you. Now, stare at the center of one of these gears and see if they appear to be rotating. You see them rotate? Very slowly. They're not rotating at all. This is not a trick. This is something happening within your brain. That's cool. I agree. What do you see? Looks like a clown? Are you sure? Let's tip it on its side. It is from a circus, all right, but it's not a clown. So again, your brain has played a trick on you. You saw something that was quite different from what, in fact, is actually there. Now, I show you these things to illustrate how easy it is for even very educated people to fool themselves. Now, most people think scientists are very closed-minded and think they have all the answers. But in fact, quite the opposite is true. The excitement in science comes from discovering new things. And sometimes things we thought were true turn out not to be true, as Albert Einstein showed us. But science does provide a way to distinguish between truth and falsity. It's not a perfect method, but it does allow us to determine that things such as these have a very low probability of being true. Now, some people believe in UFOs and even think we've been visited by little green men from outer space, but I doubt that that's the... What? But I don't think I would believe that. Astrology, which claims that the position of the planets at the moment of one's birth has been disproved in over 40 controlled studies. In fact, the James Randi Educational Foundation has offered $1 million to any one of you who can demonstrate paranormal ability under controlled conditions. So if you think you can do it, there's $1 million waiting for you. Most of alternative medicine is probably placebo. Touch therapy, where the practitioner senses and manipulates one's energy fields, is offered in over 70 hospitals around the country. And yet, it was disproved by a 9-year-old schoolgirl as part of a 4th grade science project. And she published her results in the Journal of the American Medical Association. Now, many people, in fact, who decry the use of, or decry the health hazards of electromagnetic fields, They're the same people that strap magnets to their bodies to try to cure various ills. I would be quite skeptical of that too. Now, that's not to say that people can't be affected by or even benefit from false beliefs sometimes, but if beliefs are not grounded in solid science, there is a potential for harm, and it can impede the progress of science. So it's now been 100 years since Albert Einstein has put physics on a firm foundation. And it's my opinion that it's time to do away with myths and superstition and pseudoscience, and I hope you will all join me in that effort. So I'd like to just leave you with one thought from the physicist Robert Park, who has similar views to the ones I just expressed, that we live in an orderly universe that cannot be circumvented by magic or miracles. And I would also caution you that you should be skeptical of everything that people tell you, even the things I've told you today. So with that, I would like to do one last demonstration. And for that, I will put on my hat, and we will bring out a container of liquid nitrogen, the same nitrogen we used with the methane. And we're going to force nitrogen gas into this container. That will drive the gas up where it will cool the air. The moisture in the air will condense, and it will form tiny droplets of liquid water. And that, in fact, is what we call a cloud. And so with that, I thank you all for coming.